Once again, big thanks to the organizer and to ICTS for the warm hospitality. Okay, so today I would like to talk about a couple of results that I quoted in my previous lectures, and maybe I will discuss them a little bit more. And one result which I didn't talk about, but somehow has something to do with designs, and that can be used to prove things about design. So maybe we'll see at the end. Okay, so the first result has to do with this Euclidean approximation of kernels. So let me remind the statement. You have this function h, which is defined on the real line. It's even, smooth, and compactly supported. And then using this function, you define a kernel. So this lambda, so here I didn't write the subindex, but doesn't matter. You're adding up on all the eigenvalues of the Laplacian. And you are taking only those who, imagine your function h is supported between -1 and 1. So basically you are only taking your eigenvalues between 0 and r, and and then you have this is the kernel. So the first you can think of it as this as an expansion. You only consider the first term, and the first term, in this first term there is this function q, which is okay. This is smooth and positive. This is very important. And also in xx, it equals to 1 or a constant, depending on the normalization. Then you have this term, which is basically you can call it the Euclidean term, because you just take the function h and you take the Fourier transform, the d-dimensional Fourier transform. So how can you do that if your function is even, where you basically think of it as a radial function in Rd and take the d-dimensional Fourier transform? This is also radial, so again you can think of it as a function in one variable, and this is what appears here. And then you have a remainder, which is smaller, and it is smaller because you have a power d-2 here instead of d, and it decays quickly as soon as the distance of y to x becomes bigger than 1 over r. Okay, and of course the same thing happens with this function here. So this is the statement. Notice that, as I mentioned the other day, if you pick the function h very carefully, then you can make sure so that this is perhaps positive if you wish, and this fd of h is also positive. So you can find a positive kernel, you can define a positive kernel up to some remainder that can be controlled by means of this term. So the proof is very technical, so let me just say a couple of things. So the idea is to synthesize your kernel by means of the kernel of the wave equation. I mean that this is the wave equation, and then you take this problem. So you want that at time 0 the solution is f of x and the derivative is 0. You call cosine t square root delta the kernel of the operator that sends the function f to the solution to the problem. Okay. And of course, it's easy to see that this kernel has this expansion. You can write it like this. This is a distributional kernel. And basically, when you integrate this, you get the Fourier transform f hat of m times this term. So this is the multiplier, basically. Okay, so this is the kernel in the case of the manifold. You can do the same thing in Rd. So I will just write Rd down here. And these two things are very closely related. There is this, this is called the Hadamard's parametrics for the solution to the wave equation. Basically, this kernel can be approximated just but only for a small time by means of the corresponding kernel in RD and other radial distributions. So you have this, the first term, which is just the one that we saw before, the Euclidean one, multiplied by a Q0 function, which is a smooth function. And then you have some remainder. And basically what happens with this distribution B nu is that it gets more and more regular as nu increases, up until if you take M sufficiently big, then the final remainder will be regular, but again, you have to take T small, and you can control it uniformly in time. So uniformly in XY with this term that depends only on time. Okay, so this is the idea. So how does it have anything to do with the kernel that I said before? Well, the idea is formally the following. This is your kernel, okay? And then you can write H as the one-dimensional Fourier transform of its Fourier transform, basically. So you take F1 of H and then take the cosine transform. This is even, so you can do it. Now you switch integration and sums. This is all, you can justify this, but just to do it quickly, just take F1 of H outside, and what you have here is exactly the kernel that we said before. So basically what we are saying is that you can write this kernel as a, so imagine you have H phi M F hat of X, of M, sorry, F hat of M. So this would be the solution to the problem. Sorry, this would be just the kernel applied to the function. Then you do the same thing here and you obtain the solution of the wave equation. And what you are doing is you are somehow averaging the solution in time, and you are averaging by means of this the Fourier transform of H. So this is how you synthesize your kernel, and now you can use your expansion, and basically you replace this manifold kernel with a Euclidean kernel. And well, here you can switch the Fourier transform to the second part, and it just so happens that this Fourier transform is computable. And another thing that happens is that what you obtain here is exactly what you need to, this is the definition of the Fourier transform of a radial function in RD. So here it was a one-dimensional Fourier transform, but this is the basically what the Hankel transform corresponding to the dimension D. And so this is the, of course, there are many things that have to be fixed. One is that if you want to apply this thing here, you need F1 of H to be compactly supported in minus epsilon epsilon. But of course, if H is compactly supported, then this cannot be compactly supported. So you need to work a little bit with this. You take the convolution of this with a function with a one-dimensional compactly supported Fourier transform, etc. And then you approximate. And in the end, everything works, and what you get is what we said before. So this is, I guess, the the best I can say about this problem. More than that would be just going into very, very technical details. I think that the idea is what you see here in this slide. So the second problem, second result that I mentioned is this has to do with area regular partition. So let's recall what was known. So you take sufficiently big n, then you find a partition of the sphere into n regions of equal measure and small diameter, meaning that the diameter is smaller than a constant times n to the minus 1 over d. As I said, this has been used by several authors, Tolasky, Becken-Chen, Burgen and Lindenstrass. And for the proofs, well, the idea is that more or less these authors didn't even bother to prove it, they just use it. But if you want to find the result with a small constant c, then have to be a little careful, and so you have some proofs. In dimension 2, the extension was done by my co-author Paul Leopardin in his PhD thesis, and then a different proof was given by Feige and Skekman in 2002. So this is a picture of the construction of Rachmaninoff, Sach, and Zeus. As you see, this doesn't give you a convex region because you are using your parallels. So, but anyhow, they were not interested in that. They were interested in having a small diameter. Okay. No, this is not. If you want it convex, you need to have a great circle, and this is not a great circle. This is not. So this one is not convex because this side is. Okay, if you take the distance of this point from this point is realized going through the pole, basically, like in a plane, right? Through the polar. Okay, so the proof I will present today is a little bit more general than what it would be needed in the case of a manifold, and it holds for all Alford's regular metric measure spaces of dimension D. By this I mean a complete metric space with a Borel measure such that all open balls with radius smaller than the diameter of the space have volume controlled above and below by a constant times r to the power d. So this is essentially all that we need if we want to prove this result. Of course, examples are the compact connected Riemannian manifolds like the sphere, and of course many others, but just to emphasize that this is the case in Riemannian manifolds. Okay. This is the theorem. So if you have an Alford's regular metric measure space of dimension D and you want it connected and with finite measure, then for any integer, you have a partition of your space into n regions of measure exactly, well, the measure of the whole space, think of it as 1 by n, and each one is contained in a ball which has essentially radius n to the minus 1 over d and contains a ball with the same, essentially the same radius, okay? So not only the diameter is as small as it can be, but it in fact contains a ball of essentially the same diameter and is contained in a ball of, again, the same diameter, the same radius, okay? So for our proof, we need this, at least for the case of Alford's regular spaces, we need this result, the dyadic cube decomposition of space. So this theorem, Guy David proved in 1988, and a little later, Michael Chris gave a direct proof. By this I mean that Guy David proved it for Alford's regular spaces embedded in Rn. And then there is a theorem that allows that shows that every space, every Alford space can be embedded into Rn. So it was an indirect proof somehow, and then Michael Chris gave a direct proof in spaces with a little greater generality. Okay. So what does it mean that you can have a dyadic decomposition? So you have a collection of subsets of X. You have two indices, one is alpha and the other is K. So K is the generation of the family and alpha is the index that tells you what cube in each generation you are taking. So what you have is that when you fix your generation, you cover your space, so each generation covers X. The intersection of two cubes of the same generation is empty for every generation and for every couple of disjoint cubes. When you increase the generation, you have smaller and smaller cubes. So, and also every cube is either contained in a cube of the previous generation, or it has empty intersection with that cube. And every cube contains a small, I will call it inner ball of radius A0 2 to the minus k. So every cube of generation k contains a ball of this measure and is contained in a ball bk, I will call it outer ball, of essentially the same radius multiplied by a constant A1. And these constants are always going to be the same no matter what generation and no matter what cube in the generation. So if your space is has finite measure, then your cubes, when k is negative, perhaps are going to be always the same. So this is q1 minus 1. q0 will be again the same thing, the whole space, and then you start dividing. So k is equal to 1, you have this, k equal to this, etc. Okay, so this is the usual dyadic decomposition, but in a generic context, this is the definition. So one thing that we need in our proof, and then it's actually a corollary of the above the decomposition, is this result due to Sierpinski. If you have an Alford's regular metric measure space of dimension d, and you have a set, a measurable set in X with finite measure, then for any real number between 0 and the measure of these sets, you can always find a subset of that set which has measured exactly t. Okay, and this is true for all non-atomic measures in general, but and it has a proof that due to Sierpinski, and you might need the results from functional analysis, or you might even need the choice axiom. But here you can in this context you can prove it for just using the dyadic decomposition. You can imagine how you can do it. There's nothing fancy about this. Okay, another lemma that we are gonna use is that the following. So you fix a generation and take a cube in that generation, and then you take the union of your cube with all the neighbors. So what are the neighbors? The neighbors are all those cubes such that the outer ball that contains your cube and the outer ball that contains the other cube intersect. So these are cubes which are somehow close to our starting cube. And well, you can imagine this union is contained in the ball with the same center as q alpha and radius and triple radius. This is just a geometric. And this your cube is the union of your cubes is contained in the union of the balls, as because of all the balls intersect the ball b alpha k, and all the balls have the same radius. Then of course this union is contained in 3 times the original ball. So this gives us an idea of the vicinity of cubes. And here we go with the proof of the theorem. It's very geometric, so I have some pictures. So first of all, I assume that mu x is equal to 1. So we have a little simplification of the whole thing. Now, you fix your integer n. This is the number of regions that you want. The measure is going to have to be 1 over n. So now you call little n the greatest generation of cubes, of dyadic cubes in X, such that the measure of every cube in that generation is going to be greater than or equal to 2 over n. So as the generation increases, the volume of the cubes becomes smaller and smaller. You want that each cube here is at least twice the measure of the regions that you want. So this is the first step. Now you take a graph, and this graph has as vertices the centers of the outer balls of each of these cubes. So for example, for this cube, this is the outer ball, this is the center, and you repeat that for every cube. And then the edges are between vertices that correspond to neighboring cubes. So this way you have a big graph, and it can be proved that if your space is connected, then the graph will be connected too. So for example, assume that the neighboring cubes are just those which are just adjacent to your cube, and the graph would be this one, okay? Then you take a spanning tree of your graph. So the spanning tree means that a tree which has vertices, all the vertices of the original graph are vertices of your tree, and well, it has to be a tree, okay? You can always do that. And of course it has leaves, means that, well, those green dots here are the leaves. It means that, yeah, basically you only have one edge attaching to that, vertex. Okay, so this is the spanning tree. And now you mark one point as the root of the tree. Just take any of them. Maybe, I guess you can even take a leaf if you want. And then you direct your tree from the leaves to the root. So the idea is that now we are going to show how to create regions of of volume 1 over n inside each of the cubes, and we are going to do it starting from the leaf. And because this cube doesn't have the exact volume, so that exactly 75 regions of measure 1 over n fit there, you're going to have a reminder. And the idea is that what remains here, you attach it to the following cube. And then you go on like that until you get to the center or to the root, okay? So how do we do it? Take any beta here. This is a cube. And then we know that the measure of the union of all the cubes which are neighbors to beta, and such that alpha comes before beta in the tree. So in this case are these two cubes, where the total volume is going to be smaller than C over n, where C depends only on the space. And this is because we said that all these cubes are contained in the neighboring balls, and those are those are contained in the ball center at beta with a triple radius. So that volume is controlled by a constant C over n, and that C doesn't depend on anything except the space. So in particular, in this in the union of all these cubes, at most C disjoint sets of measure 1 over n can fit, of course, because the volume is C over n, smaller than C over n. So this is the biggest number of regions that can fit here. So now the next step is you fix an integer k, which will depend only on the space, such that all cubes of generation m plus k, call it just m, has measures smaller than 1 over Cn. So all these cubes are much smaller than the original, although comparable in size, because k is fixed. But each one of them has measure smaller than 1 over Cn. Okay, we will see how we use that. So now begin with the proof. Let us start with a leaf. So let's assume that alpha is a leaf of generation n. So this is the cube that we are considering. And well, because we know that the measure of R cube is bigger than 2 over n, this is what we said at the beginning. This is how we constructed this square, but smaller than C over n, then this cube can contain a number of cubes n alpha, which is strictly between is between 2 and C. So this is the n alpha is the maximum number of cubes of measure 1 over n regions of measure 1 over n that fit inside this cube. So what we're going to do is we can just take n alpha cubes of generation m inside q alpha n. So these 3 small cubes, in this case n alpha will be 3 in this picture. Okay. The total measure is going to be n alpha is bounded by this number. So the number is n alpha, and the measure of each cube was smaller. Sorry, was smaller than 1 over C to the n. So the total measure is going to be smaller than 1 over n. So each one of these cubes has measure smaller than 1 over n. The total measure of the cube is bigger than 2 to the n. So what happens is that the measure of the remaining part is going to be greater than or equal to 1 over n. So the next step is the following. We take a region, we start from the remainder. So we take a region which has exactly the measure of the whole box, the square. Now I will call it x alpha n, just because later I will call it like that. But this is, in this case, this is only q alpha n. This is only the cube. And you take a region which has measure exactly the measure of the cube minus the total measure of the squares of the regions that you are building inside. You call it W alpha n, and this will be the remainder. It is important that you build your remainder inside the cube, because then you will have to attach it to the following cube. So, and now what you do is you extend each cube in such a way that the region that you obtain has measured exactly 1 over n, and you can repeat it for every region, and eventually your algebra works. So you have 3 n alpha regions of measure exactly 1 over n inside your box. This means that the measurement is correct and the diameter cannot be bigger than what you're looking for. You have this reminder. So what you do is, well, take a generic cube, which is not a leaf. So for example, this one, of course, you will have a reminder piece here coming from this leaf, and you might have a reminder here coming from this other node. So this is the region that now you're going to have to treat, which, as you see, is bigger than a cube. But even so, it's not a problem, because you can still repeat the same argument, and basically you start taking the reminder inside the cube, and then taking small cubes in the origin in the cube q alpha here, sorry, q beta, did I write there? Q beta n, okay, so this is the cube is q beta. And then you extend, and when you extend, you include all these triangles here, which were the remainder of the previous regions. This can be done, it's just the same argument, and I'm not going to repeat it, but it works just as well. So eventually, this allows you to construct all your regions. So the idea is dyadic decomposition plus putting some ordering in your dyadic cubes. This idea appeared in Feige-Skekman paper in 2002, where it was done for the sphere. And what they didn't need was, of course, the dyadic decomposition. You can do it with other arguments. And so what we did it here was in by using these methods of dyadic decomposition. Okay. So. Yep, exactly. And the last result that I wanted to talk about today is this inequality, Cass's inequality. So let us begin from the, say, classical case. For any choice of n real numbers, x1, xn, and for any positive integer, capital X. So you take the exponentials and you evaluate, so fix an n between 1 and x, and then you take these exponential sums. J goes from 1 to n, sum e to the 2 pi I m xj, and you square it and you add up. So this is controlled from below by essentially n times x minus 1 over 1/2 n squared. So of course this is very precise, but here we are going to be a little sloppy. So first of all, we are going to take x much bigger than n, so that basically this minus 1/2 to the n squared terms is it's really it doesn't really matter, and we will disregard precise constants. So the equality can be simplified like this. So this quantity is greater than or equal to c and x. And notice that here I'm starting with m equals to 1. If m is equal to 0, what happens? You have this is simply n squared. You just get n inside and then you square it. So if you start from n equal to 0, here you will have plus 1/2 n squared. And again, if you take x much bigger than n, here it just doesn't matter. So it doesn't really matter if here I start with m equals 0 or m equal 1. So let's see a quick interpretation of this inequality. First of all, inside the absolute value, you can throw the integral between 0 and 1 of the exponential, because they of course are 0 as long as we take m bigger than 0. And then you divide by n, you take the n inside, this is what you get. And what else? Also you divide by x. So just waving your hands a little bit, you obtain this inequality, becomes the inequality here in the third line. And so how can we think of this inequality? So no matter how well I choose my points xj, the corresponding Riemann sums will give me an error of order at least 1 over square root of n when we test these points on the first x exponentials, at least in little L2 average. Okay. So in other words, this is a result that says that, again, if you take n points, they cannot be too well distributed in some sense. This is the sense that we intend here with this inequality. So Montgomery has several generalizations of this inequality. First of all, you can put weights here, omega j. And so instead of having omega j equal 1, you just plug in omega j. And instead of having n, you have this sum here, sum of the squares of the weights. And another generalization he did was considering higher dimensional cases. So you take n points in the two-dimensional torus, and for any couple of integers x1, x2, such that the product is much bigger than n, if you take your exponential sums and your vector sum live in a rectangle of area x1, x2, then you have this inequality. This is greater than or equal to Cn and the area of the region where you take your frequencies. Okay, so this result has been previously generalized to manifolds. So Billig, Dye, and Steinerberger proved this version. So as usual, we are in a manifold, the usual notation, x1, xn is in your manifold. You take them as you want, take any weights. Then what you do is instead of taking exponential sums, of course, you take the sums of eigenfunctions evaluated at your points. You sum as the point varies, and then you take the square, and then you take all eigenfunctions up until the eigenvalue equal to L. And so as before, what you want is the d-dimensional. So before we had, remember, it was the area of the region x1, x2, where your eigenvalues were living. So here what you take is the number of eigenfunctions that you are taking. And as I mentioned the other day, by Weil's estimate, the number of eigenfunctions is going to be approximately L to the D. So what happens is that they didn't get the inequality exactly as it was before, but they have this logarithmic loss here. Okay. And in fact, it is easy to show that there is a choice of points such that this quantity is approximately equal to this. So this inequality is not sharp. Or it's sharp up to logarithmic transgression. Okay. So as Alex Josevich always loves to say, when you prove such a result, you say, well, I prove I have a sharp result up to logarithmic transgression. When you remove the logarithmic, you say you have a dramatic improvement. So our dramatic improvement is that we remove the logarithm. Okay, so we have the sharp Cassels-Montgomery inequality for manifolds. This is joint work with Luca Brandolini, Bianca Gariboldi. So, and the idea of the proof is actually rather simple because you can repeat the proof in the classical case. I didn't show it to you, but it's pretty similar to what I'm going to do now. So we can just do it in this case. First of all, assume without loss of generality that your weights are in decreasing order. So omega 1 is greater than or equal to omega 2, etc. And then let us call x the number of eigenfunctions with eigenvalues smaller than or equal to L. And as I said, this number is essentially L to the power D. Then now what we do is we take an area regular partition of M. So M is the union of UI. I goes from 1 to X. Each region has volume 1 over X. And each of them contains a ball of volume X to the minus 1 over D. And you also have the outer ball. So I'm going to give a simpler proof of the real proof. And the idea is that I'm going to assume, for the sake of simplicity, that my points xj, that can be any collection of n points, actually is such that each region ui contains at most 1 point xj. So this is the assumption that I'm going to make. Remember that I'm supposing that L is much bigger than N. I have X regions, so I have a lot of regions. I have way more regions than I have points. So each region has to contain at most 1 point. The proof for the case where every region can contain more than a point is not very different. You only have to be a bit more careful with your estimates, but it goes through anyway. So I will call Vj the region that contains the point xj. Okay. So now we are gonna, so we already used this result on the balls. Now we're going to use the other result on the approximation of the kernels. So let us take H. This time has to be a smooth, even, compactly supported function on the unit interval, or -1, 1. And what you want is that the function itself is smaller than or equal to 1. You want that the Fourier, the d-dimensional Fourier transform has to be greater than or equal to 0. And so as we mentioned before, this kernel is equal to a first term. Notice that Q was positive, and now I choose H so that FD of H is positive too. So this first part here is positive, and then you have a remainder of this order. So this is the quantity that we are going to estimate, sum of exponential squared. So because H is smaller than or equal to 1, we just throw in H of lambda m over L. So this is, of course, something smaller. And well, why? Well, here I have lambda m smaller than or equal to L. Well, this is included in the fact that H is supported in -1, 1. So when lambda m is greater than L, this is just 0. So this is in fact smaller than what's on the left. Okay, so now I open up this absolute value. I have two sums, one in J, one in K, omega J, omega K. And so after switching things a little bit, here I have exactly the kernel that I had in the previous page. And so because of the identity of the expansion that we had before, this is just equal to this first Euclidean term here, and then I have a remainder, and because everything is positive, I can say that this is bigger than the first part minus C times this remainder here. So this is the principal part. Of course, if I was able to show that there exists a positive kernel, I wouldn't have this remainder, and this would be a very simple proof. It would be finished here. And why is that? Well, let's take the principal part. So you have some J goes from 1 to N, K goes from 1 to N. And since everything is positive here, I can just take J equal to K. So this is greater than or equal to sum J goes from 0 to M, K is equal to J, so you have omega J squared, L to the power D. And then again, because J is equal to K, you have Xj equal to Xk. This is 0, so you have FDH of 0. And of course, you made this in such a way that this quantity is positive. And so this is exactly the estimate that you needed. L to the power D times sum of the square of the weights. So all you need to show now is that the remainder is in fact smaller than the main term. Okay, let us see this. Okay, so this was the remainder in the third line. So I need to distinguish between regions which are near and of each other and regions which are not. I said that the region Vj is say near Vk, and I will write J squiggle K. If the distance of the centers of the balls, of the outer balls of my region are smaller than or equal to CL to the -1. So let us look at this quantity. I can divide this sum into two pieces. So in the first case, I will take only for each J, I will only take those Ks such that Zj is close to Zk. And in that case, because xj will also be close to xk. These are points in the regions, just as zj and zk are. So this is smaller than 1 over L, essentially. So this is smaller than 1. And I can just estimate this whole term with L to the power d minus 2. There's nothing better I can do. So I just take L to the d minus 2 outside. On the other hand, if j and k are far apart, then I keep this term. I have the L to the d minus 2 outside, but I gain something by means of this. Because, of course, this is bigger than 1, essentially. Okay. So how do we handle the first part? Well, the idea is that there is only a uniformly bounded number of balls Vk near each ball Vj. Okay. This is by measure ideas, but I mean, this is just a matter of the measure of the regions and the balls. And also we know that Vj is greater than or equal to Vk whenever k is bigger than or equal to j. And so when we are estimating this quantity, by the way, here I'm not starting from k equal to 1, I'm starting with k equal to j, simply because this quantity is symmetric in j and k, so I could just take k from j to n. Okay. So I have j goes from 1 to n, and then I have at most k or kappa, this Greek kappa here, number of k's such that k is close to j, and so I will have some for these kappa terms of wk, sorry, omega k is smaller than omega j, and so I again have the estimate that I wanted, only instead of L to the power d, I have L to the power d minus 2. And well, the other term is more or less similar. You just make a dyadic decomposition of the distance. I think I will skip this part. It's really not a big deal. I mean, you just have to take your distances between xj and xk being essentially L minus 1, 2 to the s, and then add everything up, and you get again the same estimate, which is of course smaller than the one we had before. So this is the end of the proof. As I said, this is rather simple. What you need is this inequality, this expansion of the kernel, and since Billig, Dye, and Steinerberger didn't have it, they had to use the heat kernel, but the heat kernel, of course, is not compactly supported on the Fourier side. So you have a reminder, and the reminder was not small enough. So they had this logarithmic loss. Apart from that, the idea of the proof is always the same. It comes directly from the proof of Montgomery. Okay, and okay, I would like to mention an application of this result. The application is yet another answer to Giuseppe's question from the other day. So you take L bigger than 0 and assume that there are n points, xj, and weights, such that for all eigenfunctions corresponding to eigenvalues smaller than L squared, you have an identity. So this is basically a design, an L design, okay? It's just that usually you call it a design when the weight is 1 over n. So in this case, it's just generic, but let's still call it a design for today. Then what we can show is that there is a constant independent of L of n such that this inequality holds. And then by applying Cauchy-Schwarz, this shows that C L to the D is smaller than or equal to n. So if you have an L design, then you cannot have more eigenvalues than this quantity here. Okay. So this proves that the extension to manifolds of Bondarenko, Radchenko, and Vyazovskas result on the sphere was in fact sharp. And for that, you can prove this by means of the Castle's inequality. So you take this polynomial. So you take all eigenvalues smaller than L squared, and the coefficients are just taken equal to this sum of eigenvalues. And what is the integral of this polynomial? Well, just write it down, switch your sums with the integrals, take everything outside, and you have the integral of the eigenfunction, which is of course 0, unless m is equal to 0. But in that case, you only have the sum of omega I, and the sum of omega I has to be 1 if I want this to be a design. So the integral of p is exactly equal to 1. But because this is a polynomial of degree at most L, then we just said that for those polynomials, the integral coincides with the Riemann sums, with the numerical approximation of our integral. In this case, they just coincide. And I write what pxj is. So you put an xj here in place of x. And so if you notice, this is exactly the conjugate of the sum of in I is the conjugate of the sum in j. So you have the sum for all eigenvalues smaller than or equal to L of the exponential sum squared. And Castle's inequality says that this is exactly greater than or equal to C L to the power D sum of omega j squared. And this inequality is exactly the content of the theorem. And I guess that's all. Thank you very much for your attention.